Synthetic Data Generation for Small Data Orthopedic Radiology by Oliver, Max, and Ethan. Our primary research motivation was to address the data scarcity issues faced in medical imaging tasks, and our approach was to use machine learning models in order to generate synthetic data. I was focused on training curve characteristics and image realism. Oliver was focused on identifying suitable metrics, and Ethan was focused on CGAN training stability and image diversity metrics. Our methodology involved a data preprocessing step where several image preprocessing techniques were applied to the data. Oliver performed numerous tests on a variety of metrics in order to determine which were most suitable. I fine-tuned the latent diffusion-based models, and Ethan developed and trained the GAN-based models.
The evaluation of image quality metrics for radiographs involved testing their sensitivity to common imaging effects, including rotation, cropping and padding, uniform noise, and JPEG compression. In addition to this, the peak memory usage and runtime of these metrics were evaluated for a fixed set of images. Finally, the convergence behavior of sample size sensitive metrics was evaluated. From the results of these tests, we can answer three questions. Which IQA metrics are robust to common imaging transforms? How did the computational efficiencies of widely used IQA metrics compare? And at what sample size do size-sensitive metrics reliably estimate image quality? Answering these questions led us conclude that MS-SSIM and MMD were the most useful in this context due to their robustness, efficiency, and reliability.
As can be seen here, the GAN-based models demonstrated poor learning curves and significantly underperformed the diffusion-based models. Flux demonstrated the best learning curve and the highest scores out of all the models. These are sample images at specific epochs for each model. The diffusion-based model showed the most realistic images, but Stable Diffusion struggled with blending the mask and image at epochs greater than 20. It was theorized that the learning rate of Stable Diffusion was too large. My conclusions were that due to poor learning curves and model scores, the GAN-based models were ill-suited for medical data generation. That Flux outperformed Stable Diffusion in terms of all metrics and showed a better learning curve. The success of diffusion models was due to their better use of information through image masks, which allowed them to generate focused and accurate images.
The left figure shows how the CGANs were outperformed by SDXL in terms of distributional similarity. It is important to note the worsened TACGAN results in comparison to the ACGAN. The right figure represents how close the synthetic datasets were to the real training data. Unlike the CGANs, SDXL samples congregated much closer to the training data, suggesting memorization. Based on the results, although the TACGAN displayed partial improvement over the ACGAN, increased mode collapse left much to be desired. Additionally, a quality-diversity trade-off can be observed, thus resulting in neither model producing the criteria needed to address the medical data scarcity issue.